All right. Good evening, everybody. Once again, we are live and right. Let's quickly solve this without any ado. So we were doing programming yesterday, if I'm not wrong. Let's switch back to the other subject, the data structures. Then we will do one subject per hour, and we will loop it. So we don't get bored and all. So this is a binary tree. Okay. Every node has either 0 or 2 children. Okay, so it doesn't have one children, so that is basically a complete binary tree. And let n be the number of nodes. What is the number of nodes that has exactly 2 children? Even if you do not know the formula for the number of binary trees, you can actually do this pretty easily. Okay. Day 11. It's day 11. Now, all right. Yes, we are here. So this is the binary tree that those people are discussing about. So here the number of vertices is 1, 2, 3, 7, and exactly 2 children nodes is 2. So which is actually giving 7 to 2, right? And let's do one more thing. Or maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 should give something like 3. So 7. Alright, n minus 2 by 2. If you take the normal integer value, it is 5 by 2, that is 2.5, so that is 2, and 9 minus 2, 7 by 3, that is 7 by 2, that is 3.5, that is actually 3. So 5 is giving 2, 7 is giving 3, and this here is the answer, right? So yeah, this is the actual way of solving. We know this from graph theory. Yeah, this is full binary tree, not complete binary tree. Both are different. Right, this is just a problem solving approach, and 10 minus 4, 15, 30, 25, 60, 19 are inserted in the order set to okay into an initially empty binary territory. Let t be the number, let t be the resulting, okay, the number of edges in the path from the node containing 19 to the node of t is the number of edges in the path from the node containing 19 to the root node. Yeah, I missed that one. So we just need to BST implementation. Easy and 1 mark. Okay, 10 and minus 4 is smaller, so it will be minus 4, and 15 it is greater, and 30 will be here, and 20, right? So 15's greater, 20 and 5, so yeah, 5, 60, it will go all the way down, and 19, 15, 30 smaller, 20 smaller. So this is 19. So the number of edges in the path, there is only one path, 1, 2, 3 and 4. 4 should be your answer. If it is not, I don't know what it is. The answer will be 4. Yes sir, we got it. One easy question from set 2, and that's great to hear. A meld operation on two instances of data structures combines them into one single instance of the same data source. Unsorted double linked list, okay, with a pointer to the head node and a tail node of the list. Min heap implemented as an array. Binary search tree. Worst case time complexities for meld operation on instances of size and of these data structures. So, wow. Which one of the following? But there are three, alright, on two instances of data structures. Okay. So meld operation on this. So let's get the double linked list drawn. I kind of understood the question. So this is the unsorted double linked list with pointers to head and tail node of the list. So if you were to alright, combines them into one single instance. Two linked list. I think unsorted is not necessary. It was never told to sort it. So two linked list can be sorted in an average time of O of 1 if I am not wrong. And min heap. So min heap has a constraint. Yeah, unsorted is important because sorted double links, merging them takes a lot of time. I mean more time than O of 1. So this option is eliminated. And min heap. So combining two min heaps. Okay, never thought of it actually. Oh wait, min heap, right? 5, 7, 9, 11, 12, 13, something like that. And you see, and something like this, 5, 70, 90. So if you were to combine these linked lists, how much time would it take? I mean, O of, okay, I don't know. Binary search tree, combining two binary search trees. Okay. What is meld operation on data structures? So it is a valid name. So if you were to, put 50 in the appropriate position, maybe 1, 3 and 5. Let's do that. So 1, okay, I don't know. Melding to unsort. Yeah, we got that one. For min heaps, we can concatenate two heaps and run a build heap. Okay, which takes often time. For binary trees, the optimal method in order traversal of both trees. Yeah, the binary heaps do not concatenate the two underlying arrays. Build heap. So you need to know something about build heap. I mean, no matter how many reference books you read, you are not going to get this one. I can say that. Preserving the original tree structure. Only the result is a valid BST. Perform in order traversal of both trees to obtain two sorted arrays. Merge two sorted arrays into one. Wow, my guy did something. Okay. So when yeah, I mean 2 marks. I can see why it is 2 marks. And operation. At least we got the double linked list one right. Consider stack data structure into which we can push and pop records. Assume that each record pushed into the stack has a positive integer key. Okay, and all keys are distinct. We wish to augment the stack data structure with one time in operation that returns a pointer to the record with the smallest key present in the stack. So you can update it by comparison without deleting the corresponding record and without increasing the complexities of the standard stack operation. So push and pop operations, alright. Let's say you push 20 and min is pointing to this one, and you can compare 10 and 20 in linear time and min is pointing to this one. Let's say you did 30 and you are comparing 10 and 30. It is pointing to this one and you did 5. You will just compare 10 and 5 and min will point to this one. So keep with every record and stack a pointer to the record, the smallest key below it. Okay, keep a pointer to the record with the smallest key in the stack. So record is pushed and each record pushed into the stack has a positive integer key and all keys are distinct. So pointer to the record with the smallest key below it. But the keys are never said to be in ascending order if I'm not wrong. Record. Okay, you are thinking in the wrong direction. Positive integer key. Record with smallest key. So this is correct. Auxiliary array in which the key values of the records in the stack are maintained in sorted order. Complexities of standard stack operations, but it increases the space complexity. Keep them in heap. So A and B should be correct. If min gets popped, you need to rescan to find the next min. Okay, if min gets popped, you need to rescan this. Store with each block, with each node a pointer to the minimum. Okay. Keep with every record in the stack a pointer to the record with the smallest key below it. Keep a pointer to the record with the smallest key in the stack. Okay, wait. I got it. So this main pointer should not be in this record. It should be in this record. Right, but let's say if you popped this min element and the next min is 10, so you need to rescan that. But the pop operation technically complex it is. Okay, it never increased the. Okay, so for this portion, the smallest element is in top and the pointer to the min is stored in the below record, and the smallest element is popped. Rescan the stack to find the smallest one. So technically pop operation increased the time complexity of no, that is a stupid doubt. Alright, I understood it. So you need to assume, alright, put everything into consideration. So binary search tree having undistinct integers, the maximum length of the path from the root node to any other node is n minus 1. So this is going to be the maximum path, right? Nice. The in-order traverser always produces sorted sequence of elements. That is true as well. Finding an element takes over log 2 of time in worst case. Binary search tree. So you need to give the worst case. So skewed. So this is CD and false. A, B are true. Yeah, we got it. Thank you. The height of the router tree is defined as the maximum number of edges in the path from the root node to any leaf node. The height of the alright, spoilers ahead. The height of the rooted tree is defined as the maximum number of edges in the path from the root node to any leaf node. Suppose the min heap stores 32 key elements. So we already did this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is 1, 2, 4, 8, and down you will get 16. 3, 7, 15. 15 plus 16 is 31. This 32 will be in height 1, 2, 3, 4, 5. Right, this level will have 16 and this level will have the 32nd one. Yeah, height of the tree is 5. Yeah. It is flagged for some reason. In int main. In int main and while condition pointer one is there. We kind of did this one before, but let's do it again. Find query in list while list is not equals to null. If list of data is equals to query, return 1, list will be list of next. So find is just doing the linear search kind of thing. And pointer 1 is equals to L1, pointer 2 is equals to L2. Okay. And while pointer 1 of next is not equals to null, so query gets the pointer 1 of next of data. If query is found in L2, pointer 1 of next will point to the point. Alright. See, this is updation part. This is looking up part. I kind of missed that one out. So let's do this 1, 7, 12, 3, 9, 5, 11, 15, 8. I remember doing this one by the way. 1, 11, 6, 9, 15, 12, 1, 4. How do I remember? Because I thought I would fit a long time. Pointer 1 of next is not equals to null, okay? Query is equals to pointer 1. So this is where pointer 1 is and this is where pointer 2 is initially, and this is the query. If query is found in L2, no query is not found in L2, so pointer 1 is now pointing to this one. So you will go on like this. Now query is this one, so 12 is found in the list. So now pointer 1 will point to pointer 1 of next. So this happens, right? And now pointer query will be pointer 1 of next of data, this will be query, and is 9 found? Yes, 9 is found, and so it will do this. And now this will be our query. Is 11 found? Yes, 11 is found, so it will do this. And now what? This is going to be oh wait, this is where we messed up, it seems. Yeah, so pointer 1 of next. Alright, we are at, this is the query, 9 is the query. Okay, and we found 9 in L2. Since we found that, we are going to update this pointer 1 of next to this one. And next what? Okay, pointer 1 of next. Okay, so this next part is going to update to this one, but still the pointer 1 is pointing to this one. So still the pointer 1 is pointing to this one, yeah. So pointer 1 of next points to this one, and this next he will search for this one. So 11 is the query, and it was found. It was found. So pointer 1 of next will be updated to so you need the next part. Let's assume these are the next parts, and this is pointer 1 now. Pointer 1 of next is not equals to null, so query is equals to pointer 1 of next of data. This is query, and you found query. No, you did not find query. So now pointer 1 will be updated to pointer 1 of next. So this is pointer 1 now. Now what? Query is pointer 1 of next of data. So this is your query, and 12 is found. Yes, 12 is found. And what will you do? Pointer 1 of next. This will point to pointer 1 of next. This is pointer 1 of next, and this is next of next. Yeah, now pointer 1 is still here. Got it? So pointer 1 of next is not equals to null. Pointer 1 of next is pointing to this one, so this data, this will be query. Now is this found? No, it is not here. So now the pointer 1 will be updated. Got it? Yeah. If the data is found, it is going to skip it. That's it. And now what? Query is pointing to this one, sorry. This one, my bad. So this is what the query is pointing to now. And is 9 found? Yes, 9 is found. And you will update this one like this. And still the pointers here, got it? And now pointer 1 of next is not equals to null. So did you find the 5? No, it did not find the 5. So now the pointer 1 will point to this, and I don't care about this one. Now 5. So this is going to be our query, and is 11 found? Yes, 11 is found. So this will be updated. Pointer 1 is still there. And now is 15 found? Yes, 15 is found as well. So pointer 1 of next will point to pointer 1 of next of next. That is it. 8. 8 is found over there. No. So pointer 1 will move here, and what there is pointer 1 of next is null now. So this is going to be that the number of nodes that will be null one. So you will have this node, you will have this node, you will have this node, this one, and this. You won't have this, you won't have this, you will have this. 1, 2, 3, 4, 5 nodes will be over there. Okay. 1, 7, 3, 5, 8. Yeah, we kind of got it. So that is all about the 2025 question. You are given a set of 8 distinct integers. Nice. A binary search tree is created by inserting all elements one by one, starting with an empty tree. The tree T follows the convention that at each node, all values stored in the left subtree of the node are smaller than the values stored at the node. You are not aware of the sequence in which the values are inserted into T, and you have no access to it. All the values stored in the left subtree of the node are smaller than the values stored at the node. No, what is this guy doing? Which one of the following are right? A binary search tree. A binary search tree itself means that, right? So we need to get into the actual definitions at each node. So this value is going to be smaller than this value, and this value is going to be smaller than this value, okay? Not aware of the sequence in which these values are inserted into T. Five and 3 is going to be smaller. So you don't care about this? In order traversal. A root node can be determined. Smaller. What? I couldn't comprehend the question in the first place. Yeah, that is nice analogy. That's what I have been thinking. Okay. So this is a set, and these are the elements. Now the traversal is this. Now the tree is this, but for both of these, the in-order traversal results in 2, 3, 5, 9 only. So option A is correct, and I'm not countering it. Let S1 and S2 be two stacks. Okay. S1 has the capacity of 4 elements, S2 has the capacity of 2 elements, S1 already has 4 elements, S2 is empty. Push to S2. Only the following three options are available. Pop the top element of S2 and push it to S2, okay? Push to S1. Pop the top element from S1 and push it to S2. Pop the top element from S2 and push it to S1. Pop the top element from S1 and generate to user, okay? Note that the pop operation is not allowed on empty stack and the push operation is not allowed on full stack. Okay. Wow. Pop operation is not allowed on an empty stack and push operate. So you can generate 400 or you know what? You can just so the first valid operation is pop the top element from S1 and push it onto S2. So if you consider that one, then this will be that. This will be that, okay? And if you consider, case one, or you can just output it. So these are the two cases, and now what you can from this one, from this point of view, you cannot pop this one yet, okay? So the output can be only from so the output cannot be 100, that's for sure. And if the output is 200, 400 and 300 should be in stack for the output to be 200. Then what it is saying 300. No, it cannot be 300. Oh wait, you can push to S2. I mean, you can push to S1 and 100, 300. So then this will be the state if 200 and 300 is there. And now can you get 400? Now 400 needs to be pushed to get the generate output. So this option is eliminated as well. So if you do 400 is generated to output and 100, 200, 300, this one is there, and to generate the output of 200, 300 needs to be pushed and 200 output need to be generated. So 100, 300 will be the next state. This is satisfied, and 100 you need to kind of push this, I mean pop this, but you cannot pop into an empty stack. So you cannot get 100 after. That's what I meant. So to get this, 400 will be here and 300 can be popped out and 200 can be popped out. Uh, but at the end, but if you display like three elements, so pop two items. So it will be 400, 300 now, and now print 200 as output. Okay, pop 300 from S2 and push to S1. Okay, print 300 now. Okay, now S1 is equals to 100, S2 is equal to 400. Pop 400 from S2. Yeah, this is what I have been asking. Can't pop. No, pop is not allowed on empty stack. So on this stack, pop is not allowed. We did not mean pop is not allowed. If it makes the stack empty, then it is impossible. Okay, silly mistakes happen sometimes, and you cannot do anything. So we will start fresh. So let's do from this. To display 100, displaying 100 first is impossible. Displaying 200 first, let's see. You can do this and you can do this. So 200 will be in the console, and after that you want to display 300. So you will put into this and you will display it out. So that is possible. And now 400, can you display that? You can put into this and you can display out. That's possible as well. And 100, that's possible as well. It is a very simple question, you just complicated it. So binary min heap consisting of 105 distinct elements. Index of the maximum elements stored in the array. So the maximum element can be in only leaf node, and this is a structure. So this level contains 1, this level contains 2, 4, 8, 16, 32, total 64, right? So how many? 3 plus 4, 7, 7 plus 8, 15, 15 plus 16, 31, and this is 63. And if this level is to be completed, there should be 127 elements. So, but this level, 105 elements only. So if this level was entirely full, it should contain 127 elements. But now it contains only 105 elements. So how many elements are missing? 22 elements are missing. So, alright. So there are 22 such elements that are missing like this. So you need to, the maximum value could be any of these. Alright. So 32, how many are these and how many are these? So 22 elements are missing. So these are 11 elements. That's good. And this level contains how many? This level contains 32 elements and 22 of them are missing. So this level contains only 10. Oh wait, 64, right? 64, sorry. And this level contains 64 elements and 22 of them are missing. So 2 and 4, 42 plus 11, that is 53. So it can be anywhere from 53. It can be any of those 53 elements. Number of, okay. You can just buy 2 and get the lower bound. So they are internal nodes. I see. So 7 by 2. 3. Okay, it is simple. If you know the formula, obviously. But our analysis paid off. Which one of the following sequences, when stored in array locations, form max heap? Okay. So 23, 17 and 10, 6 and 13, 14, that's wrong. And 23, 17 and 14, 7 and 13, 10 and 1. Wait. 5 and 6, 12. So option B is correct. The Xavier told it. Yes, sir. SLL delete be a function that deletes a node In a single linked list, given a pointer to the node and a pointer to the head of the list. Okay, if you are given a head and if you are given the pointer to the node, you will delete that node. DLL that deletes node in the double linked list if the pointer of the node and the pointer of the head is given. Let n denote the number of nodes in each linked list. Oh, you need head, yeah. Worst case time complexity. So when will be the singly linked list has worst case time complexity? Let's say you deleted this last node. You need to put this previous node to null. So for that you need to travel all of this. So singly linked list delete is O of n. We know that. But doubly linked list, it's a different case. So in doubly linked list, if you let's say were to delete this node, you need to connect like this. You know from this node, you know the pointer to this node, and you know the pointer to this node. So connecting is easy. And if you were to delete this one, right? This one, you already know the value of head. So you just need to put the head to this one. This is also off and one time. So doubly linked list delete. I don't see any case. Let's say the last one. If you want to delete the last one, you just need to delete it, free the memory location, and you just need to put this one to null. It also takes off one time. So D is the answer. Yeah, it is D. We are good. It is. Let A be a priority queue for maintaining a set of elements. Suppose A is implemented using a MaxHeap data structure. Operation extract max extracts and deletes the maximum element. Insert inserts a new element. The properties of MaxHeap are preserved at the end of each operation. That's how a priority queue works. When A contains n elements, which of the following statements about the worst case running time of these operations is true? So extracting max, right? Let's make a dry run. If you extract this, you are going to delete it and you need to replace this with the next biggest element. So you will get something from here, right? MaxHeap. Wait. It is MaxHeap. So 30, 20, 10, 5, 3, 4, 2. That is MaxHeap. And either 20 or 10 are going to be the bigger elements. You don't go below them. So extracting max, just you need to replace, let's say 30 is deleted and 20 is replaced. Now 20 will not be here. Now what? You need to care about this entire one. So that entire one, caring and sorting, takes O of log n time because it is recursively cut in half. Just you need to put your 5 in here, that's it. and inserting, and let's say, all right, this is your heap and you need to insert a new element, let's say 45 here, and this needs to jump up and up until this gets thing. So O of log n again, so both takes O of log n. B is your answer. Yes, B is your answer. I just wanted to be extra confident with that question, that's it. We almost hit 1 hour. So this is a struct node. It has value left and right pointers. It is a function. Return value. If p is equals to null, return 0. Else return p of value of function left plus function right. So it is a recursive function. So p of value is 10 plus foo5 plus foo11. So foo5 is going to call 5 plus foo3 plus foo8. So foo3, alright, there is no left and right for this. So it will return, alright, 3 and 8. 3 plus 0 plus 0, 8 plus 0 plus 0 to be precise. So this returns what? 16. 16. I mean, the first one returned by it is 3 and the second one returned by it is 8. 3, 8 and 16. So that is a basic recursion and C should be your answer. Yes, C is your answer. Now you are better than what you were before. So sequence of elements, A0 is equals to 1, A1 is equals to 5, 7, 8, 9, 2. Yeah, I did this one already. Push elements of A0 to A5 in that order into stack. So you are pushing 1, 5, 7, 8, 9 and 2. So NQ the elements from A0 to A5 in that order. So 1, 5, 7, 8, 9 and 2. So pop an element from S. Popped. DQ an element from Q. DQ'd. Pop an element from S. Popped. DQ an element from Q. DQ'd. DQ an element from Q and push the same element into S. So DQ'd and pushed. Repeat operation 7 3 times. So DQ'd, popped 1, DQ'd, popped 2 times, DQ'd, popped 3 times. Pop an element and pop an element. The top of the element is 8. The top of the stack is 8. Nice. Nice. So it is 1 hour and how many questions did we do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we did 15 questions in an hour. That is good. But as you know, this speed is absolutely not enough. But we are learning. Nothing to worry about. Shall we go into algorithms? And then, another from theory of computation. Alright, after algorithms, I'll take a break and we will do TOC and compiler design and we'll call it a day. Okay, maybe TOC only, not compiler design. So we will do some Okay. Consider the following algorithm. Alright, I will take a break. Good thing actually. Right, let's do it. Consider the following algorithm that takes an undirected graph G as an input and some algorithm G. Okay, so this algorithm takes this graph as input. That B will be any vertex BFS on G starting at V, U be vertex in G at maximum distance. So how do you get the maximum distance from BFS? Breadth first search. So I just only know BFS of trees. I feel like this is going to be, I mean, any node of this level is going to be at maximum distance. Let U be a vertex in at maximum distance from V. So let us assume this is a vertex and this is a vertex. Run BFS on G again with U as a starting vertex. Let Z be the vertex at maximum distance from U. So from this vertex, if you do BFS, which element is going to be at maximum distance to you? So what will you do? No, how do you even run BFS in the first place? Output is the distance between. Push the adjacent element. Okay, maybe mark it as visited. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, and 6. So the maximum distance is just 6. 1, 2, 3, 4, 5, and 6. So from this vertex to this vertex, the maximum distance is 6 and I do not see any. So this is V and this is U, and from U to Z, 1, 2, 3, 6 is your answer. Okay, 1, 2, 3, 4. Okay, diameter, yes, that is a new term. 1, 2, 3, 4, 5, 6. Okay. It is more of a spatial coordination question. Does it work on any vertex? No, it doesn't actually. take one extreme and calculate for another extreme. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, it is a diameter question. Spelling mistake in question. Consider an unordered, okay. Unordered list of indistinct integers. What is the minimum number of element comparisons required to find an integer in the list that is not the largest in the list? This is the minimum number of not the largest. That is easy. To find the largest, it is difficult. Let's assume this is largest. Minimum number of element comparisons. So it was not asked about maximum. If it was asked about maximum, to know this is largest, to know this is not largest, right? Okay, we are assuming it is largest and it is proved that it is not largest. And let's say if we have this one, if we assume this is largest, it is proved it is not largest. Yeah, this is what I'm thinking. You need one comparison, two comparison, three comparisons to actually say okay, to find an integer. It is asking to find an integer, not to say whether if first is not largest or not. So with one comparison, you are going to get an element that is not largest. If this is the case, you are going to say this is not largest. If this is the case, then you are going to say this is not largest. So all you need is one comparison and one is your answer. Yeah. Okay, that's understood. Okay, that is a set 2 question. Which one of the following statements regarding BFS and AFS on an undirected graph are true? BFS and AFS on an undirected graph. A DFS tree of G Okay, let's consider an undirected graph. A DFS tree on G is the shortest path of G. Yeah, so how are you going to get a DFS tree? Okay, okay, and okay, you will have this. You will have this, you will get the same tree. It is the shortest path, yeah. Every non-tree edge of G with respect to we don't know what a forward or back edge. If UV is a non-tree edge of G with respect to a BFS tree, And the distance from the source vertex to the BFS tree, we don't know. Connected components. Yes, this is true. I think A and A are true. Okay. DFS tree is not necessarily represent the shortest path from the source vertex. DFS experts as part of the responsible. Okay, yeah. So tree to tree is obviously going to give the answers. Simple and directed graph. Be comfortable with graphs. So you know what? If you do the DFS tree from this to this, but if you chose this path, then 1, 2, 3, 4, and 5. So the DFS is going to be 1, and then to 2, and then to 3, and then to 2, and then to 1 again, and then to 4, and then to 5. So the DFS tree indeed gave a shortage. Is this a DFS tree? Okay, let's see. Every non-tree edge. Yep, that's messed up. It is not very great at reasoning, it seems. Why does DFS tree does not produce the shortest edge? Okay. So there is something called tree edge and back edge. Every non-tree edge. Okay. Source were text to you and we. I understood D. Alright. You need to know forward edge and back edge. Okay. Okay. Seems like a gold channel. Don't confuse me with the conversion all, brother. I don't understand the original question itself. So, okay. The thing is, you don't know much about this. An outrage with respect to DFS trace of an undirected simple graph. Somewhere I saw a cross edge. I mean, where are these people studying all of these things, man? In BFS tree, the levels of vertices represent distance from the source vertex. If U, V is a non-tree edge, then UV must be at the same level or at levels that differ by 1. Okay. So an edge exists between U and V. But non-tree. So they can be either like this, or they should be like this, or they should be something like this. That's it. They cannot be like this. Why? Because no edge in graph itself. Yeah. Okay, that is understandable. My God. That is 1, that is 2, that is 3, and that is 4. Let A be an array of length n with distinct elements. It's said to be bitonic if there exists an index 1 less than or I is less than or equal to n, such that A of 1 to I is sorted in non-decreasing order. I plus 1 to n is sorted in non-increasing order. Asymptotic bounds for the worst number of comparisons by an algorithm that searches for an element in a bitonic array. Okay, I just wanted to. I am having an urge, to put the O of n, but we need to make an analysis. So non-decreasing order. So they must not decrease. So 5, 6, 7, 8. That is non-decreasing order, and non-increasing order. So from I plus 1 to n, from I plus, okay, this is 1 to I, and from I plus 1 to n, they just need it to be non-increasing. That means they should not increase. Let's say, no man, 9, 6, 3, 2. and let's do 19 and 11. Okay, all right. So this is our bitonic array. So you need to find the worst case. Let's say finding the smallest element. Which one of the following represents the best possible asymptotic bound for the worst case number of comparisons by an algorithm that searches by an element in a bitonic array? So search for 2. 2 might be, oh wait, oh wait, I got it. So you start from here. All right, you can skip this one. You can skip this entire part and you can start from here. So the size of I was not stated, but alright. But worst case number of comparisons. If the worst case is if I is only this level, then you need to search for all of these elements. So it is often overflow again. Asymptotic bound for the worst case. So bound for the worst case. Bound for worst case. We need to know that it is a pretty standard binary search problem. It is from a weekly goddamn contest. 26 are online. What do you mean? So 26 people are studying this problem right now. Wow. I just wanted to see how many people are there that do some problem. Anyways, bitonic array increases and decreases, find the peak. Binary search on both sides. Why did I not think about it? You are thinking in linear search. Elements right to the peak element are in decreasing order. Elements left to the peak element are in increasing order. That's correct. Modified binary search. Okay, I need this example 2, 4, 5, 7, 6, 3. So from the glance, you can say 7 is the peak element, and this deserves an upvote first of all. Okay, yeah, she did it again. Study while others are sleeping. Work while others are loafing. Yo, no. She seems like a person that deserves more than 5,000 rank. Maybe she's grinding this year, I can see. She'll give gate. But she has seen more questions than me. So, yeah. So, 0, 1, 2, 3, 4, 5. Alright, mid is 2. Yes, sir, mid is 2. And 5. Okay. So, low became 3. Mid became 4, 6. And A of 5 is 3. Okay, with the elements you can see in which phase you are. I did not think about it. Bitonic array. No, literally I did not think about it. That's why it is called as the mountain problem, because the elements are growing and shrinking like this. So you need to find an element. It can be either here, it can be either here. Finding the peak takes over log n time, and searching this takes over log n time, and searching this takes over log n time. So these three searches, 3 over log n, which is over log n. Nice. Only if you made all of that analysis into your head. Okay. Let G be an undirected graph with I need to drink some milk and I need to get back. It is 1 hour 35 minutes, not too bad. And we will get back at 10:30 or something, and we will stream until 12. See ya, people. Yeah. On a second thought, I will complete this question. Undirected graph, undirected graph with positive edge weights. T with a minimum spanning tree of G for any two vertices U and V. D1 UV, D2 UV be the shortest distances between U and V in G and T respectively. Which one of the following? Okay. We did this question. We did this question actually. So consider an undirected graph. Okay, I don't want to replicate a tree here for obvious reasons, and T be a minimum spanning tree. So this can be an instance of minimum spanning tree. And for any two vertices u and v, alright, d1 between shortest distance between, okay, shortest distance between u and v, okay, g and t respectively. So if you take this case, both are equal, but that is not enough. They can be equal. You can only say that, but you cannot say. So if you take something like this, if you take something like this is smaller, this is larger, because MST is not necessarily include all edges. So this distance can be smaller or at max equal to. So this distance can it ever be greater? No, because it contains more possibilities. For all possible, for some this might be, for some this might be. This will never be true. I mean, equality is there, so all of these cases can be simulated, but B is your answer. MST may or may not be. My guy cracked it in single line. Okay. This is a recurrence relation, and we are supposed to learn about recurrence relations. Compute first few values manually. So it grows like 4 power n, but using substitution, change of variables, or the iterative expansion method. How are these open source contributing? Uh-huh. S of 2 power n. Okay. So we thought of this again. We need to learn recurrence relations. So let's get a learning path. I mean, you already covered the theory for recurrence relations. So you need to learn no matter how it takes, how much time it takes. Let's do this one and let's go. Function takes an array. For I is equals to 0 to n minus 2, for z is equals to n minus I minus 2, then swap it. The number of swap orders. So number of swap orders. I is equals to 0 to n minus 2. So 29 elements. So n minus 1 is equals to 29, n is equals to 30. So 0 to 28 for j is equals to 0 to n minus I minus 2 actually. So that is 28 it will call. And then I value will become 1 to 28, and it will again become 0 to 27. So descending order, that is 30, 29, 28, something like that. If this is greater, you need to swap this. So it will do 28 swaps. Oh wait, 0 to 28. If a of j is greater than a of j plus 1, let's do 1 to 5. So it will do n minus 1 swaps actually. Twenty-seven swaps, and it will do 26 swaps. It will do 25. So 27 to 0, n by 2 into a plus n. There are 28 terms by 2. First term is 27, last term is 0. So that is 14 times 27, 10 and 27, 378. Nope. Okay. Zero to 28 means 29 iterations. Yeah. So it is 28. That is what I did, right? It runs from 0 to 29 times It will be swapped. Okay. Okay. So I is equal to 0, I less than n minus 1, I plus plus, right? So what he did is I is equal to 0, I less than or equal to n minus 2, I plus plus. Both are same stuff. Oh my god. 29. 29 by 2 into 29 plus 0. N by 2. Okay, number of terms is going to be 30. Oh god. 29 times 15 and 5 is 45. 14 and 29. 5, 9, 4. 435. Yeah, you got it. Alright, we will solve this one. How many did we solve? 1, 2, 3, 4, 5, 6, 7 questions solved. 7 questions solved. So total 22 questions in like less than 2 hours. We need to pump the numbers up. Okay, people, I am disconnecting and I will see you people after some time. Bye bye.